In this section, we're going to go ahead and look at conic sections, two more things, ellipses and hyperbolas. Some of these conic sections we've already looked at. So when we look at conic sections, they're actually four things: parabolas, circles, and ellipses and hyperbolas. These two we've already looked at, and these two we're going to look at in this section. Now, what are conic sections? Imagine two cones, one of them upside down, touching each other like this. If you take a plane, like a sheet of paper, and you cut through the cones in certain angles, you're going to create these shapes that we've looked at and these two that we're going to look at now. So if you take these two cones and you cut through them, imagine with this plane or this sheet of paper, you're going to make this shape along the sides of the cone, bottom cone, which creates what's essentially a parabola, something like this. If you take the plane and you cut through it exactly right across, flat, you're going to get a circle, which we've looked at before. So in this case, if you go through it at an angle like this, it's no longer a circle, but it's sort of stretched looking circle, which is an ellipse, which is what we look at today. If you take a sheet of paper or a plane, in other words, and you cut through both pieces of the cones, you're going to get some curve that sort of looks like a parabola, and then the image of it exactly symmetric down below with the other cone also, which creates this shape, which is a hyperbola. So these four shapes can be created by cutting through these cones at certain angles. We've already looked at the equation for parabola and circle, and we're going to go ahead and look at the equations for the ellipse and the hyperbola as well. So these two were done. Let's go take a look at these two. We're going to look at the ellipse centered at the origin, and the way an ellipse is formed is basically if we take a string and keep the length fixed and then use maybe two thumbtacks and put them down, and if you make it really taut and go all the way around, you're going to end up making an ellipse. In other words, the distance of this piece and this piece added together is always the same. Now, what's the equation in standard form? The equation in standard form is x squared over a squared plus y squared over b squared equals 1, and you always want it to be equal to 1 because it makes the graphing easy. Now, what do the a and the b mean? A rough sketch, they're basically the vertices and co-vertices of this ellipse. So this is one of the vertices of the ellipse, and this is the other. And these are called the co-vertices. Whichever way it's elongated or stretched, that's known as the major axes. So in other words, if I go a units this way, e units this way, my length of major axes will be 2a or double a. And then the length of my minor axes, the one that's not stretched in that direction, will be 2b. So you have a major axis, and then you also have minor axes. And analyzing and graphing them is actually going to be fairly simple because we're going to be given the ellipse in standard form like this or close to standard form, and then graphing it just tells us to go basically a steps left or right from the center and b steps up or down from the center, and then you make the graph of your ellipse. And the center for us is always going to be the origin anyway. So we know the center again is always going to be 0, 0 because there's nothing with the x squared and the y squared. So we start at 0, 0. Then this 9 under the x says go 3 left and right in the horizontal direction because of this x. And then this 16 says go 4 up and down in the vertical direction because it's under the y is the easy way to think of it. And again, all we're really doing is taking the square root of 9 and taking the square root of 16 to get those values. So I go left and right 3 steps, and then I go up and down 4 steps, and just as easy as a circle, I make my ellipse. And the vertices are always along the major axes. So it's 0, 4, and 0, negative 4, and we're done. Let's look at another one. Notice this doesn't equal a 1. We want this to be equal to a 1 because that's going to make it in standard form and easy to graph. So we're going to go ahead and divide everybody by 1, and that's going to give us x squared over 4, and then y squared over 60. So now we're ready to go. The center is 0, 0, and we're going to go square root of 16, which is 4, but notice it's under the y squared, so up and down is how I'm going to go 4 steps. And then square root of 4, which is 2, and since it's under the horizontal direction, I'm going to go left or right 2 steps. So from the center, 0, 0, go up 4 steps, down 4 steps, and in the horizontal or x direction, go right 2 and left 2. So again, it doesn't matter whether it starts with a y or an x, just go the steps accordingly. And since it seems to be elongated vertically, again, we have our vertices 0, 4 along the major axes, which is the y-axis in this case, and 0, negative 4 for the other vertex. Let's look at one more. Again, I have x squared and y squared, and actually just a pointer, the way I know that this is an ellipse and not a circle is because this y squared has a coefficient positive 4 and this has a coefficient 1. If the coefficients were the same, it would be a circle. So let's get a 1 on the right side. I get x squared over 4 plus y squared over 1, I guess, equals 1. So essentially, when I don't have a denominator and I just have a y squared, I can always put my own 1 under it. That tells me how many steps to take from the center of 0, 0. So in the horizontal or x direction, 2 steps, and in the vertical or y direction, 1 step. So 2 step right, left, 1 step up, 1 step down, and that gives me a small little ellipse. And this has major axes horizontal, so the vertices are at 2, 0 and negative 2, 0. Remember, vertices are always along the stretched way the ellipse lies. The hyperbola looks a lot like the ellipse, except it has a minus in the middle as opposed to the plus that the ellipses we looked at had in the middle. And we can have 2 things happen. If we have the hyperbola start with, so x squared, it opens left and right, it only has x-intercepts. And if the hyperbola starts with a coefficient being positive for the y squared, then it only has y-intercepts, so it opens up and down only. And these are the vertices of the hyperbola. And the process of graphing it is a little bit harder, but we'll go ahead and do it step by step because they also contain asymptotes. So in graphing the hyperbola, it starts off a lot like the ellipse. Remember, it's a minus. So the center is still, since there's nothing with the x's and the y's, 0, 0. This tells me to go 2 right and left because it's in the horizontal direction under the x. And this tells me to go 3 up and down against square root of 9 in the vertical or y direction. So I go 2 to the right, 2 to the left, 3 up, 3 down. However, now I don't make an ellipse because it's a hyperbola, and actually an easy way to think of this is you can make an h with the minus for a hyperbola, and for an ellipse with the plus sign of an ellipse, you would be able to make a little e, reminding you that that's an ellipse and this is a hyperbola. Anyway, let's go back and now make what's called the rectangular or sometimes the auxiliary box. So out of the 4 dots, you make a box. That's not part of the hyperbola, but it helps you in graphing it. After you make the box, you make a diagonal through the edges and the center of the box. On MyMathLab, you probably won't see any of this. You'll just see the final graph to pick, but this is how you develop the graph. So through the rectangular box, you make a diagonal, an x, and then since this starts with an x squared, it only has x-intercepts. If you were to go let y be equal to 0, you'll be able to find the 2 x-intercepts to be plus or minus 2. So after that, let's make the actual graph in blue. You take this vertex, an x-intercept, and you approach the asymptotes, not touching them. You take this negative 2 x-intercept or vertex, and you approach the asymptotes, not touching them. Then the equations of the asymptotes, they're really just lines, y equals mx plus b, with the y-intercept of both lines being 0, and the slope just being the change in y over the change in x. So if I find the slope through this point and this point, I go 1, 2, 3 up, and then 1, 2 over. So it's the change in y, which is a 3 coming out of the y's, and the change in x, which is a 2 coming out of the x's, and you have two of them. You have y equals plus or minus 3/2 x. One of them is the one with the positive slope going through quadrants 1 and 3, the other one going through quadrants 2 and 4 with a negative slope. So we're going to go ahead and graph this hyperbola. It's a hyperbola because there's a minus in the middle. We know it has to equal 1 to be in standard form to make the graphing easier. So we're going to divide by 9. And we're going to go find the pieces in order. We're going to get the 4 dots, then make the rectangle, then get the asymptotes through the corners and the center, and then draw the branches of the hyperbola. So this tells me I go 3, since it's in the y direction, up and down from the center 0, 0. And this tells me I go 1 left and right because it's under the x and the x direction. So let's go get the 4. I got my 4 dots from the center of the origin. Then I make my box through these 4 dots, so rectangle. Then I get the asymptotes going always through the corner and the center of the box to the best of your ability. Then draw your branches. Since I have a y squared that this begins with, I must have my hyperbola open up and down, only containing y-intercepts. So again, that happens because if I try to find the y-intercepts and make x 0, I get a nice little equation, y squared equals 9, which tells me the two y-intercepts are plus or minus 3, which happen to be the vertices anyway. So I just got 2 ordered pairs, which I knew anyway because it was going to open up. I'm going to make my branches, getting closer to the asymptotes but not touching them. So there's my hyperbola in blue. Now what are the asymptote equations? Well, I have y equals mx plus b, where b I know is always going to be 0 because it goes through the origin, and that's the y-intercept being 0 for these 2 lines. The slope is always the change in y over the change in x, the rise over the run. The rise was 3 and the run was 1, so it's 3 over 1 x plus or minus, because I have a line with a positive slope and the other line with a negative slope. So the equations of the asymptotes are plus or minus 3x basically. Okay, it says let's use the graph to find the equation of the hyperbola. So I know it has these 2 x-intercepts, meaning it must start with an x squared to be able to have x-intercepts. I just have to figure out what things to find to square to put under there. Again, x-intercepts, it must start with an x squared. Well, I know I've taken 2 steps to the right and 2 steps to the left, so 2 squared goes under the x's. So far we're good with the first piece. I just have to figure out what goes under the y's, and I'll have the asymptotes help me in getting that. I'm going to use the asymptotes and find ordered pairs that make it seem like I must have this imaginary rectangle in the background. Again, I use those because none of these easily go through my grid, and this looks like it best approximates a rectangle that these branches, the left and right branches, get near. So it looks like I must have gone 3 up and 3 down, so then I take that 3 and squared and put it under the y's, so I have x squared over 4 minus y squared over 9 equals 1 as my hyperbola, because my rectangle has, or the asymptote has the equation change in y is a 3 and the change in x is in a 2. If I needed the equations of the asymptote, it would be a rise of 3 and a run of 2, but it doesn't ask for that. So we have the equation, we got the 2 using the vertices, and then using the asymptotes we found the 3 under the y's.